That's awesome. Hey everyone, yeah, welcome to my talk, Ace Up the Sleeve, hacking into Apple's new USB-C controller. Who am I? My name is Thomas Roth. I'm probably better known as Stack Smashing now. I'm a security researcher. I do a lot of hardware and firmware, and I'm a co-founder together with Live Overflow at Hackstree.io, where we try to teach low-level IT security, from reversing to hardware security to web security. Now, before we start, there's always a lot of people whose research you build upon, and so I want to thank a couple of people such as Sigusa, Ollie, who built Thunderbolt Patcher, the SI Linux team, T8012 dev team, Marc Zinier, Carlo Maragno, who's accidentally on there twice, but he deserves that. So yeah, thanks to all of these people. Without their work, I couldn't do what I did, and so they deserve a mention. Now, before we start, a short backstory. I started looking at Lightning the past few years, and the main reason for that is that, Lightning, being the proprietary connector by Apple, does some obvious stuff like charging, USB, video and audio and so on, but it can also do some cool stuff such as JTAG, UART, so serial console, STQ, and so on and so forth. And 2 years ago, I guess, we built something called the Tamarind cable, which is essentially a super cheap way to get access to these buses. So you just need a Lightning cable, a $10 Raspberry Pi, and then you're ready to go and explore these secrets of Lightning. Unfortunately, Apple decided at the end of last year to make all my work useless by doing this.
So we're bringing USB-C to iPhone 15. It enables charging, transferring data, playing audio and video.
Now, for whatever reason, in their keynote, they forgot about all the cool stuff. And so we have to figure out, can we do this? Now, USB-C has, a ton of pins, and so there must be a way to, you can do USB, but there must be a way to do much more than just USB. And then, I pre-ordered the iPhone 15 because everyone told me, oh, will this work on iPhone 15 and so on. And then I started looking into USB-C, which I had zero experience with, and I realized the iPhone is not the first Apple device with USB-C. Like the MacBooks, the iPads, and so on, they had USB-C for a long time, and there are a lot of people who already looked at USB-C on these devices. Now, USB-C is a complex beast, and so, for example, just to charge something with USB-C, you need something called a USB-C port controller. And so the USB-C port controller basically does the power delivery negotiation, so saying how much voltage, how much current, and so on you can deliver. And this is done using a custom protocol on the configuration channel pins on the USB-C connector. And this is all handled by a small microcontroller we call the USB-C port controller. Now, microcontrollers run firmware, and so the T8012 dev team found that they can actually dump on Intel Macs already the firmware of that USB-C controller. And so they wrote this awesome blog post, and one of the things they found out is that there are a lot of secrets in that USB-C port controller. So it doesn't just negotiate, charging and so on, but it also supports something called VDM, vendor-defined messages. VDM is essentially a way for vendors to allow custom things to be communicated via USB-C charging without using the actual USB protocol. And the T8012 dev team found that there are a couple of actions they call Apple VDM that allow us to reconfigure the USB-C port on MacBooks. And so, for example, we can map the serial console to the SBU pins, and we can also map different other buses. So, for example, an I2C bus, and so on and so forth. And to do that, we just need to send this VDM action over there. Internally in the MacBook, this works by basically we have the Type-C port controller, which on Apple we call the ACE, because that's just the string in the firmware everywhere. And there are multiple versions of the ACE depending on your type of MacBook. And so, for example, on the latest MacBook, it's the ACE 3. On the previous, like M1 MacBook, it's the ACE 2, and so on and so forth. And the ACE has multiple connections to the system on chip. So, for example, there's USB and Thunderbolt, as mentioned, serial console, and there's also stuff like JTAG, and so on and so forth, which is really cool. Now, how can we actually send these VDM commands? Because they are not USB, right? You can't just use libUSB to send VDM. Instead, you actually need hardware support, or hardware driver support at least, to send those. And a couple of smart people found that you can reconfigure the back left port on the MacBook to actually be essentially a debug probe. And so you can use that to send VDM commands and so on. And Marc Zinier also built a dedicated hardware device to essentially get a serial console on a MacBook. Now, I wanted more than just the serial console. I wanted to interact with debugging ports, JTAG, and so on and so forth. And so I forked the central scrutinizer, and I called it Tamarind C. And essentially, this allows us bidirectional access to the internal buses on the iPhone. Using this, we discovered that the SPMI bus is used on the iPhone. It has JTAG probe integrated, and overall, it's pretty nifty to explore USB-C Apple devices. I have a couple of these boards with me, so if you want a bare PCB, let me know after the talk. And in the end, you have a setup like this, with my logic analyzer connected here too, and then you can do fun stuff such as, get a serial console on your iPhone. So on the left here, we have the control channel. Then I can just say VDM reboot, which reboots the phone, and I get a nice serial console of the iPhone. This is not big news, but what happened afterwards is that I got interested in this chip, the ACE2. And now the ACE2 is actually a Texas Instruments chip, and it's an ARM-based microcontroller connected via I2C. You can find it on MacBooks, starting with the first MacBook with T2, I think. And it turns out that this is just a customized version of a TI chip called the TPS65986. And unfortunately, all the details on how to write firmware for it, how to patch it, and so on, is all under NDA with Texas Instruments. And so you only get a rough data sheet, you get some leaked documents that describe some things, and so on. And so you have to dump the firmware. Now, obviously, nobody gives you the dumped firmware, and so I had to open up my M1 MacBook and basically solder on some wires and get this out. The nice thing is, for most older MacBooks, you can actually get reconstructed schematics, and so it's easy to find these pinouts, right? You have almost no work to do, you just solder and done. Now, when you analyze the firmware, you find that there's a gigantic command handler structure. And there are a couple of interesting commands. So for example, there's commands that are named memr, memw, and mem, which sounds like peek and poke to me. But unfortunately, these are privileged. And so if we had an engineering device, we could actually read and write memory on this port controller. Turns out these are all locked on production devices, unfortunately, but we can still send commands to the chip. And this is done using the Apple HPM bus. So I think host port something bus. And it's essentially an internal I2C interface that lets us communicate with the chip. And it uses these 4 CC commands, so you have 4 letters which are converted into an integer. And I built a small tool to communicate with the ACE this way. And so we can send arbitrary commands, we can send arbitrary data, and we can see what we get back. We can also see, which is pretty important later on, the status that the chip is in. And so for example, the regular status is application. If we reboot the chip, it goes into boot. If it has a broken firmware, it goes into DFU mode. Now, this chip has an external SPI flash, and there are actually multiple USB-C port controllers in a MacBook. And they're kind of daisy-chained, and so only one has a SPI flash, and then the others boot from the main chip, so to say. Now, unfortunately, if you dump this chip, it doesn't actually contain firmware. Instead, it contains patches for the integrated mask ROM in the chip. And this makes reversing freaking annoying. So even if you dump the chip, in the end, let's say you have a function in ROM and you want to see a function call, you go into that call and it's another function, which then just dereferences a pointer which comes from the external flash. And that one is loaded into RAM. And then the address this patched pointer points to can then either be in ROM or in RAM. And that actually gives you the actual implementation. So this breaks all cross-references in your decompiler, and so on and so forth. And you have to manually, I had to build some scripts to make this easier to work with. But yeah, it's really annoying. They use a really weird compiler that does really messy optimizations. At least it seems so to me. So yeah, not fun. And you have thousands of these function pointers that you get to reverse engineer. You can also, from macOS, reflash this chip. And so what we can do is we can use a tool called USB-C Firmware Flasher that comes integrated with macOS, and we can use this to reflash the external flash. Unfortunately, these updates are protected, and so they are signed with RSA 3072. But this only is checked during update, and so we can actually reflash the external flash, and we can boot our modifications. This is not really useful because, you know, opening up a MacBook and reflashing the port controller, like you can, at that point, you can just put in a bug, like a physical bug. However, I still found an attack that allows me from software to attack this chip, reflash it permanently, and this actually survives full restores. And this means that essentially, if you hack this chip, there's no way to get rid of any malware in there. And it's connected to a USB. It can control the USB-C data lines. And so you can do a couple of fun things. So let's say you have like a checkmate-style exploit. You can actually tether this, right? It will, as long as the chip stays compromised, you can just re-compromise the main controller. However, the ACE2 is on its way out. It doesn't do a whole lot, and the iPhone 15 uses a different chip, namely the ACE3. The ACE3 is also a Texas Instruments chip, but it's completely custom seemingly. There's zero public information. In fact, there's so little information that I tweeted about one of the chip serial numbers, and that started like the gray market people who sell leftover controllers of the factories in China. They started contacting me and offering me money so that I write a product description for this chip. So yeah, that's fun because you essentially get zero help. Nobody knows what's going on. And it's used in the iPhone 15 and also on the MacBooks with M3 Pro and Max chips. Now the ACE3 does much more than the ACE2. It actually runs a full USB stack. And so when you restart your phone in DFU, it actually goes into this port DFU mode. And this one, you basically interact with the ACE first, give the ACE firmware, and then you can actually get the SoC into DFU. Now, unfortunately, ACE3 doesn't use USB-C firmware flasher, and also the updates are personalized. So they are heavily cryptographically signed. They are different for each single ACE. Like even each ACE in your MacBook has a different signature, it seems like. And so I was very curious to see how this works. And so I ordered a MacBook M3 Max, tried my vulnerability, and it doesn't work, obviously. So they changed everything, and unfortunately, my vuln didn't work. And now I can either send the laptop back, or, you know, I mean, I don't think Amazon checks if the device has been opened, so. So I opened up the MacBook Pro. And what's nice is, like, this was relatively close to the launch of the device, and so there was really no leaked schematics. There was nobody who actually probed the device publicly, so I had to do all of this myself. You can actually see the ACE3 on the left here, and another ACE3 on the right, or actually the debugging ports on the right here. And if we zoom in on this, the actual debug ports look the same to what we saw on the ACE2. It's very similar, and when you measure it, it's actually almost the same pinout. And so we have the ACE3 here, we have the SPI flash here, and then these debug connectors. Now, the nice thing about the ACE2 was that the debug port was enabled, so you could just solder on some wires, talk to the chip, dump it. So I used needle probes to get access to this connector, and the debug port is disabled, unfortunately. Okay, so let's dump the flash. So I reverse engineered by probing with a logic analyzer all the lines. And I used the needle probes on a microscope to get access to these tiny flash pins, because I didn't want to solder, because I want to send it back to Amazon, so theoretically. And I found that, yeah, I get access to the flash, I can dump the flash, but unfortunately, it's, again, the same. It's just small patches. It's not firmware, it's not full code, and so on and so forth. And after staring into the hex dump long enough, I was able to reverse engineer the header format. I found a couple of CRCs and so on. And I thought, hey, okay, nice. I would just, previously they didn't signature check the flash contents, so I just changed them, fixed the CRCs, and I get it hacked. Nope, doesn't work. Now, there are two chances here. Either I just missed a very simple additional CRC or something, or they are good at engineering, or most likely both, unfortunately. So I ended up basically using my old software vulnerability. I tried to find physical SWD access. I tried modifying the flash contents. I tried fuzzing, and I actually found a timing side channel that lets me enumerate all supported commands by the chip. So it takes a bit longer to respond when a command is invalid, essentially. But yeah, nothing to get actually to get the firmware out. And so we're in a situation where we have a completely undocumented chip. We have no firmware. We have only some simple commands like, reboot and so on and so forth. So time to give up? Nope, because, there's this awesome magic technique, fault injection. And the idea behind fault injection is that we can introduce faults into the chip. So for example, using a laser, we can flip bits. And that allows us to modify the behavior of the firmware that is running on the chip. Unfortunately, it also has the minor side effect of often killing chips, which is bad if a single chip costs you 2,500 euros. So there are multiple types of fault injection. For example, there's voltage fault injection, where we essentially use a very short drop in the voltage. We basically short circuit the power supply at a very precise amount in time, at a very precise moment in time for a very precise amount of time. Unfortunately, this requires soldering, removal of capacitors. You need to reverse engineer the schematic to find the core voltage, and so on and so forth. It's a pain. Like, to do this on a logic board the size of a MacBook, like, this is easily multiple weeks with multiple people just to find the core voltage. However, there's also something called electromagnetic fault injection. And EMFI is essentially, we create a high voltage pulse, like 300 volts, we send it into a coil, and then the electromagnetic field will collapse into the chip and inject voltages at precise locations on the chip. And this can allow us to effectively, the side effects are we can skip instructions, change register values, and so on. Now, we can't deterministically change them, but if you change a 0 to a 1 or to 1,000, it's still true suddenly, so you can change logic conditions this way. Also, no target prep is necessary. So all we do is we take, in my case, a chip shouter, we point it at the chip, we bzzzt it, and then the chip is hacked. Theoretically. The big problem is we need to have super precise timing on when to inject our chip. And we know nothing about the boot chain, right? We know 0 on when this check happens, and so on and so forth. And so we need another way. And there's another nice magical hardware thing called side channels. Now, I wanted to do this as cheaply as possible. And so I wanted to use an EM side channel. So essentially, I want to, when the transistors in the chip switch, you get electromagnetic emissions, right? And we can measure those, for example, with like a small coil. And then normally you would use a high-end oscilloscope, but I decided to just use a cheap SDR for like 100 euro or so. And then I used one of those PC bytes, and I just taped the probe on there and just dropped it on the chip. And this allows us to capture the magic chip waves. And so hopefully we can use this to determine when to glitch the chip. And if we actually look at the spectrum, while we reboot the chip, we can actually see very significant emissions here. And this is cool, but also useless, because this could also just be the spy bus of the flash or so. And so we need to actually look at this in a lot of details. And so my idea was, I start recording the spectrum on the HackRF, I reboot the ACE3 using my ACE tool, I get the electromagnetic recording, and then I stare at it for a while. And so I created this gigantic Jupyter notebook, which does like FFTs and so on and so forth. And eventually, I was left with a nice trace. This trace looks fine. The problem is that each recording will have a different offset, because we don't have a perfect alignment. So we can fix this in software, right? Like we can just align the traces. However, the HackRF also has a trigger input. And so if we find a good trigger signal, we can actually very nicely time this. And if we zoom into the flash trace, flashes use a chip select line. And that chip select line will drop low as soon as the chip starts, because it will start loading from the flash, and we have a perfect trigger. So we start recording on the chip select, we reboot the ACE3, and we get a perfectly aligned recording. In theory, this looks somewhat like this. There's also a trigger inverter on the left, and then we just probe the CS line with a needle probe, and we have our electromagnetic probe, and then we get perfectly aligned recordings. In fact, they are so perfect that if you look at it on like a video, there's almost zero noise on the horizontal axis, which is the one that matters. And so this really works well. Now, you might also recognize that this is actually these big spikes perfectly align with the flash. And so we actually get very nice timing, like we can confirm that, okay, we see something. But how do we use this side channel to time our glitch? Now the idea is simple. We change the firmware, we take another recording, and then we compare the differences. Now, sounds easy, but every time you have to replace the needle probes on the microscope, try flashing it till it works, because at least my flash programmer can't, like every 10th attempt works. Then you reset up the hardware setup, you do the measurement, and then you repeat. Now, when we compare the original firmware with the modified firmware, which doesn't boot successfully, we can see that there's a very significant difference in the trace at the very beginning after the flash load. And so we can see that our side channel actually indicates something about the boot process. Now, the problem is we don't know what it indicates and whether this really gives us a good timing. But remember that we reverse engineered the CRCs already. And so theoretically, if we fix a CRC, the boot should take longer to fail, right? Because the first CRC check succeeds, the second one succeeds, and so on and so forth. So I tried that, did the original firmware, used the wrong first CRC, which, no difference. Used the second CRC, no difference. But then when the first two were correct, we can see that the boot fails much later in time. In fact, it's so late that it's very likely that the whole check of the firmware is happening somewhere before this. And so easily enough, we just glitch here. Perfect. So normally, for EMFI, the location on where you put your probe is very important because, the die is huge and so you want to be very precise. And so normally you use a nice like CNC XY table and so on. Unfortunately, I managed to fry mine just before Christmas. And so instead, I just rested my chip chowder on some camera batteries and just used a gigantic coil to cover the whole chip. And, then we have a nice setup. We have a chip chowder. We have the trigger connection for the chip select line. We have our chip whisperer, which we use for triggering and pulse creation. We have a ground connection, and we have days of debugging and wasted time. Now, this photo is a lie. This is how it actually looked. Gigantic mess of cables. And so the first attempt is, we want to change the version string and see if we can get our modified firmware to boot, right? Because we don't know, like maybe there's additional checks, maybe this is not easily glitchable. And the nice thing is that via HPM diagnose, you can get the version string of the ACE3 firmware. And so I just took that 5, I replaced it in the firmware with a 2, reflashed that, and then we just arm the Husky and the chip chowder, reboot the ACE3, wait for the glitch, and then we check whether the chip is running in app or in ADFU. If our firmware failed to boot, it will be in ADFU. If we successfully booted our modified firmware, it will be in app. And then we repeat this for hours on end. And so I wrote a simple Jupyter notebook that essentially controls all of this. And the laptop is actually glitching itself. So it's like a very, very weird thing because we need access to the ACE command line. Now the troubles are massive because sometimes the ACE3 completely stops responding, and then we need to reboot. So we need to implement an auto reboot. After the reboot, if the ACE3 doesn't charge, the MacBook doesn't charge if the ACE3 is bricked. And so we have 8 hours of attempts. Then we need to reflash everything, charge the MacBook up, and start over. You do this for a couple of days, and eventually you end up with success. And if we then, dump the firmware version, we can see we successfully modified the firmware version. So we glitched the ACE3. Nice. We changed the version number, which is completely useless. And it doesn't really help us, right? Because we only know the patches that are loaded from Flash. We don't know what the patches actually patch. And we have no input or output. So even if we get code execution, we don't know how to control the pins of the chip to, for example, get us the data out. And so I was thinking maybe I do like an EM side channel and a tied loop that bit banks it out or something. However, we do have the ACE2 firmware, and it's very likely that there's at least one command that will be more or less identical between ACE2 and ACE3, and maybe we get lucky, and that command was patched in the ACE3 somehow. And so I started looking at all the functions in the patches that I could find, and eventually I found that something called the USB-W handler seems to be patched on the ACE3. And so if I replace the patched version in the flash, I boot it, I call the USB-W command handler using ACE tool, I can actually run and control my code. And even better, I can return data to my host. And so I can use this to get data out. So I replaced this large function with like 6 or 7 ARM instructions, which basically just load the address that I sent to the ACE, and then it returns it to my host. Super, super simple. Days of debugging still, but hey. And so attempt 2, we again start glitching, and after a couple of hours, we get success. And then we can use ACE tool to send this USB-W command. And I just want to see whether I can read address 0. So we do that, and we get a result. Now, who recognizes what that result is? Who does a lot of ARM? No? Address 0 is the reset vector. This is actually the initial stack pointer value. And so we successfully can read and write arbitrary memory on the chip. We actually managed to get code execution through magic magnetic waves on the ACE3. And so time to dump, we can dump a whole 4 bytes at a time. And so this takes hours and hours and hours. And remember, the MacBook doesn't charge while I do this sometimes. And so I had to do this over like multiple days with like a lot of attempts and so on and so forth. But eventually I had a full dump of the ACE3 ROM and RAM and so on. And now we actually managed to reverse engineer some of the boot functionality. We can emulate part of the ACE3 and so on. And so essentially it's possible with relatively off-the-shelf equipment to dump completely unknown silicon, right? We knew almost nothing about this chip. We just knew something about some minor details about the predecessor. And it's not super difficult. You need endurance for sure, a persistence, yes. But we don't actually need, I don't know, a focused ion beam, a scanning electron microscope, or anything like that. But we can use electromagnetic fault injection to do this relatively easily. And now we can start researching the ACE3 in more detail, and there's some more stuff to come there. So with that, thanks a lot. Hope you enjoyed this. Yeah.